In this video, I'm going to try to go through homework 1, and in the process, I'll try to cover some of the mathematics that I'm expecting you to know before taking the course. So that being said, I understand that some of you haven't taken Calculus 2 and Algebra 1, so that's okay. I'll try to give a brief review of these things that I need during the lectures, and also I will record separate videos on these mathematical concepts, and hopefully it will be enough as a review of the things that you need to know. So let's get started with question 1. So instead of doing this on my website, I generated a PDF and I will do it here instead so I can write on it. So let's start with the first one. It's a series sum. So this will be useful like right after the midterm, but we'll do it here anyways. So this expression, you should write it out. So it's 7 times 0.5 to the power 1 plus 0.5 to the power 2, and so on until 0.5 to the power 25. So this looks like this geometric sum, which we have a formula. You don't need to remember the formula, you just need to know that there exists a formula. And it looks like it, but there is a 1 missing, so let's put the 1 in front. So 1 is 0.5 to the power 0, basically. And we added 1, so we need to subtract 1 at the end to balance it out. So this part, we know the formula 1 minus 0.5 to the power 25 is t minus 1, so t is 26. And divide by 1 minus 0.5, and this subtract 1 multiplied by 7. This, but whatever this is in the answer, you'll be okay. So the second one is an important concept about normal vector. I will use a 3-dimensional example. This also applies to higher dimensional case. So in lecture 1, I actually talk about this. So this minus 4, 2, and 2 is called the normal vector. Let's actually draw a plane. So we have a 3-dimensional space, say x1, x2, and x3, and we have a plane here. And there is a vector such that every vector on the plane is perpendicular to that vector. So this is called a normal vector, and normal vector given the equation is always the coefficients. So we have this. So we basically ignore the constant term. What I mean by perpendicular is if you pick a vector, any vector on the plane, not a vector from the origin to something on the plane, a vector that's completely on the plane, then that vector will be perpendicular to this normal vector. So to see why this is true, we can actually pick a vector and say that vector is from A, B, C to say D, E, F. So we know that ABC, this ABC vector and this DEF vector, they are both on the plane. So these two things should satisfy this equation. So if you plug them in, you will get minus 4a plus 2b minus 2c is minus 5 is 0, and minus 4d plus 2e minus 2f is also minus 5 is also 0. If you take the difference, you see minus 4 a minus d plus 2 b minus e and minus 2 c minus f. This is 0. So these two constants cancel out when you take the difference between the two expressions. So what this expression is just a dot product between minus 4 to minus 2 transpose dot a minus d, b minus e, c minus f. So when I say dot product, x dot y is just x transpose y, so they are basically the same thing. And their dot product will be 0. So what it means is this will be a vector. So this is the difference between 2 points. So it's a vector on the plane. And this is the normal vector. So that's why the normal vector dot any vector on the plane is 0. When the dot product of two things is 0, these two vectors are perpendicular. So you can view this statement as a definition, but you can also see the dot product is also, I remember, the cosine of the angle between the two vectors. So I guess it's actually more complex. And then you can, from that, is the cosine of the angle in between. From that, you can figure out that they are 90 degrees to each other, so they are perpendicular. In any case, we know that the normal will be this thing, and the question is asking for the unit normal. So we need to know how to calculate the length of a vector. So the length of a vector is just the, I would say just the norm, but norm is it's not clear what it is as well. So I'll just write down the formula. So it's just a squared plus b squared plus c squared. That will be the length of a vector. So the length of this vector is not 1. We want to make it 1. So a unit vector means length 1 vector. So we can just divide this by the length. So this dividing by 4 squared plus 2 squared plus 2 squared, or whatever the resulting thing is, you put it here, it's the normal vector. I mean the unit normal vector. Okay, so let's move on to the third one. The third one is asking about the Hessian matrix. I usually pronounce it as Hessian, but many people pronounce it as Hessian. Anyways, the Hessian matrix is the second derivative matrix. So if you have a one-dimensional function, so for example, y is x squared, you have the first derivative is 2x, second derivative is 2. So second derivative is a number. But if you have two variables like this, the second derivative is no longer a number because you have two variables. So that second derivative is a matrix and is called the Hessian matrix. So the first derivative, by the way, is called the gradient. We'll use this a lot throughout the term. But let's actually get the first derivative first. So the first derivative is, we want the derivative with respect to x and the derivative with respect to y. So let this function be f. Then df dx, df dy, actually x1 and x2. This thing is called the gradient. So if you take the derivative of f with respect to x1, this would be just 2x1, and that part will be 0. And also, if you take derivative with respect to x2, then this will be 0, and the other term will be minus 6x2, I guess. So if we are evaluating this at a particular point, the gradient at that point would be, so at 2 minus 5 would be 4 and 30. So that's the gradient, but we're not asked to find the gradient, we're asked to find the Hessian. So the Hessian function, I mean the matrix here, is the f derivative with respect to x1 twice, and then with respect to x1 and then x2, and with respect to x2 and then x1, and with respect to x2 squared. I mean twice. It should not be called squared. So we need to evaluate these 4 entries separately, and these 4 would form a matrix. And that matrix is the Hessian matrix. And let's do the first one. Differentiating once is 2x1, so differentiating twice would be just 2. And differentiating with respect to x1 and then differentiating with respect to x2. So basically this expression differentiated with respect to x2, is 0. And similarly, this is first derivative with respect to x2, which is this expression, and then you differentiate again with respect to x1 now, is also 0. So usually for most of the continuous function that we will see in this course, these two values are the same. So, but anyways, let's do the last one. The last one is differentiating with respect to x2 twice. So differentiating once is this, differentiating again is minus 6. So the Hessian matrix is just 2, 0, 0, minus 6. I guess that's all I want to talk about. There is the complexity problem, but I will talk about it in the actual lecture instead of doing it here. So the next one is just an exercise in chain rule, how to take a derivative with respect to a function of one variable. So we want to differentiate this thing with respect to w. So the w. So we want to use the chain rule. The chain rule basically says we take the product of the derivative of the outer function multiplied by the derivative of the inner function. So the outer function is this 1 over something function, and the derivative of this is minus 1 over that something squared. So I usually make it exponent. So this is just 1 over x is x minus 1. So the derivative is minus 1 times x minus 2. So that means the derivative of the outer function is this thing squared. Oh, there's a minus sign. So minus, this is minus 1 over x squared. So the x is the whole thing. And you also need to multiply it by the derivative of this x, so of the inner function. So the derivative of this is 1. Derivative of 1 is 0. Derivative of this is itself. But this is a small inner function, so we'll decompose this into two parts. One is e to the sum y. So e to the y derivative is still e to the y. When you differentiate exponents, it's still an exponent. So we will have the derivative of the outer function, and we multiply it again by the derivative of the inner function, which is this small thing here. And the derivative of 4w times 3 is just 4. So at the end, we multiply the three terms together, and you get the derivative here. So again, the chain rule just says derivative of the outer function multiplied by the derivative of the inner function. And this is a huge function. This is now the outer function, the derivative of the outer function times the derivative of the inner function. So that's basically chain rule. So when we do neural networks in week 2, I will talk a lot more about how to write the chain rule expression. But for now, you just need to know how to use the chain rule to do these derivatives. So now let's move on to question 5. So question 5, I think, is an interesting question that shows you if you work in 1 to 3 dimensional spaces, it's actually very, very different from higher dimensions. So the question is asking if you put 2 to the n number of, say, spheres, basically in 1 dimension, a sphere is just an interval. So this is a sphere in 1D. And this would be a sphere or circle in 2D. And in 3D, it's actually a sphere. So if you go to my website, and you can rotate this, you can zoom in a bit, you can see that there are 8 spheres surrounding the blue sphere in the middle. So let's get back here. So we have 2 to the n of these, and we put a blue sphere in the middle. And we're asking, what's the size of this? So the specific question is asking, when will this blue sphere, part of it will be outside of this red box? You probably think it's impossible, but since I'm asking the question, well, it is possible in higher dimensions. So we will start with 2-dimensional case, and then you'll see why. So here, suppose we are in 2D, then I think the assumption is the radius here is 1. So this radius is also 1. And so this radius is also 1. So suppose we want to find the distance between the center and the center of this sphere. It will be, this is 1, this is 1, so this is square root 2. Right? So if we have 1 and 1, this will be square root of 1 square plus 1 square, which is square root 2. So this whole length will be square root 2. Let's draw the part circle here. So this length will be the radius of the blue circle. So this length would be, note that this is also 1, right? Because the radius is always 1. So this blue circle radius, so the blue radius is square root 2 minus 1. So if we look at the 3D version, it's harder to see it here, but if you imagine the point at the center, and then you go along x 1 unit, go along y 1 unit, and go along z up 1 unit. So if you draw two triangles like this, the distance between the center and the center of one of these 8 spheres would be 1 square plus 1 square plus 1 square. So this length would be square root 2, and this length would be square root 2 square plus 1 square, so it's square root 3. So now, the tricky thing is that if you look at the gray sphere, the radius is also 1. So that's why the blue sphere, if you look at it this way, the blue sphere, the radius, so the blue radius is square root 3 minus 1. So there seems to be a pattern. And let's go back to one dimension. One dimension, the two spheres would push the blue sphere, actually it's a dot. So the dot, the size of the dot, so the blue dot radius is 0. And 0 is actually square root 1 minus 1. So it seems the pattern is that the blue sphere radius, so also in higher than 3 dimensions, no longer called a sphere, it's called a hypersphere. But in any case, it's square root n minus 1. Now let's look at the boxes. So in 1D, the box size is, this is 1, this is 1, so it's 2. In 2D, this is also, this is 1, this is 2, this is 4. I think I'm getting it wrong. So the radius here is 1, so half of it is actually 2. And here, the other half of it is also 2. So basically, the box size is 4. And here is also 4 by 4. And here is also 4 by 4. The z direction is also 4. Because if you look at the spheres, this is 1, 1, this is 1, 1. So they still sum up to 4. So half of this, so it's like the radius of this red box is always 2. So red box, quote, radius is basically half of side length, is always 2. So at some point when n gets large, this expression will be larger than this. So we want to find for what n, for which of these n, this is true. So you can try to calculate this. You can substitute all of these numbers here. You can figure out which ones. In how large the dimension will be in order for the blue sphere to be outside of the red box, which sounds surprising. But if you look at the first 3 dimensions, at the beginning, it's very small. It's basically 0. When dimension is 2, it gets larger. When dimension is 3, if you look at the diagram, it's actually larger than the 2D version. So in each dimension, the sphere gets larger and larger. And eventually, if you imagine a very high dimensional space, this will be so large that it's outside of this bounding box, this red bounding box. Okay, so that's enough of this. So the next one is asking about the spanning tree. And this will be useful also after the midterm, but I will talk about it now. So suppose you have a graph like this. A spanning tree would just be a tree that covers all the vertices. So we want a tree that covers all of these vertices. And a tree, what I mean by a tree is each node has at most one parent. So, and I think we're using the convention that parent point to their children. So a parent can point to many children, but each node can only have one thing pointing to it. So one example of a spanning tree is you can point to 1, point to 2, say point to 3, and point to 5, and we can actually do anything. So we'll do 2 point to 4. So if you actually draw this as a tree, then this is 0 and 0 pointing to the children, which is 1 and 5, 1 pointing to the children, which is 2 and 3, and 2 points to 4. So it's a tree like this. And the next question is just so it's related to the drawing probability stuff, but it's not obvious what's going on here. So I'm using this just for a fun exercise to fill in the squares. So we want the row sums to be 2, 1, 2, 3, 1, and column sums to be 5, 1, 0, 2, 1. So 5 here is obvious because there are only 5 boxes. We need to color all of them red. And 1, so these two are 1, so there's already 1, so we don't need to add anything. So here it's 2, so we need to add another 1. And also this is 1, so we don't need to add anything in this column now. And we need to add 2 things in this column, so we can color these 2. And last one, this needs a 3, so we can color that one. So you can always color the square sequentially like this. There are multiple ways to achieve the same column sums and row sums, so any version should be okay. And question 8 is just testing whether lines can be drawn correctly. So we're just drawing a line. So here is actually not a good idea to do it here. So let's move back to here and maybe move to here. We can draw a line and it will become a straight line. If you draw another one, you will replace the previous one. So I'll do the last one here as well. So the key thing here is basically knowing a directed graph can be represented by its adjacency matrix. So the adjacency matrix is actually very easy to read. I actually put a hint here. So here it means node 0. There's an edge between node 0 and node 0, 1, 2. So let's actually put down 0, 1, 2, and 3 here. And 0 would point to 2 because there is a 1 here. And the second row would be node 1. Node 1 points to 0. And node 1 also points to 2. And the third row is starting from 2. 2 also points to 0, so it's harder to draw. So you can draw a curvy line and it will become a curve, so it does not cover the other one. And 2 also points to 3, so you have this. And at the end, the last row corresponds to node 3. 3 points to 2, so I'll draw it like this. And 3 also points to 3 itself. So you can start from here and basically put a circle. So you will map back to itself. So that's question 9. And I think that's all. Question 10 is just enter whatever you want.